Thanks for coming, and I appreciate you taking the time to listen to this presentation. What I'm going to try and do this afternoon is lead you through an exercise. So I want you to see how you can participate in actually bringing together individuals from different disciplines. And I understand that many of you are planners here today, as well as working for utilities, stormwater scientists, engineers. So this exercise will be an attempt to show you how you can use a decision support tool that we've developed at Ecology, the Puget Sound Characterization. So there's benefits for taking this approach, benefits in the sense that you're able to coordinate efforts and you're able to look at what an overall plan might be before you really start getting down to the specifics of designing stormwater facilities, where they'd be located. In particular, what I want to do today is that I'm going to talk about our water flow models. We have water quality models, but I'm just going to focus pretty much on the water flow models and the relationship of process, structure, function. Yeah, that's very appropriate. And the example, which will be in Blackjack Creek, which is in the Kitsap Peninsula. So many of you are probably familiar with process, structure, and function. How many have heard of that before? Okay, many, so this will be new. So when I'm talking about processes, I'm talking about the movement of water above, through, and discharging in the landscape, in a watershed. So that process is the movement not only of water, but of sediment, heat, wood, carbon, energy. And that movement actually has a profound effect upon structure. And probably the structure that you're most familiar with is the structure that you see in streams in terms of its asymmetrical nature, that you have woody debris that's entrained, you have sandbars, you have, because of the operation of the thawag, you will have different gravels of different sizes. And that diversity in the structure actually promotes niches, so those niches become then habitat for invertebrates, and then forms the base of the food chain, which supports, of course, as you all know, our higher organisms that are in there. So at its very core, if you're able to duplicate or at least protect and maintain these processes, the normal range and flow of water patterns within a creek or aquatic system, the more chance you're going to have at maintaining the diversity of that particular aquatic system food web. So one of the things that we all know happens within these systems, they're very dynamic. So that dynamism is hard, particularly to model, particularly when we're looking at climate change that is coming upon us at this point in time. But in addition, we have threats or stressors which are generated by humans that we all understand are probably overshadowing a lot of these climate signals at this point. So an urban area will have far more effect in terms of its impervious surface than will actual climate in itself. So this is why the emphasis, as you all understand, is necessary to develop some type of modeling effort that can attenuate the effect of the impairment to these process, structure, function relationship. So this very boring diagram here is one that I hope that we can use more and more. These 4 steps are one that's essential to doing any sort of watershed plan. And unfortunately, we don't follow through on using this in most sort of watershed approaches. The first is characterizing, understanding how that watershed functions. So today we're just going to look at the water flow processes. When you examine those, you then come up with a general idea of where you might prioritize the type of solutions that you think will work within that watershed. We're going to look at that in Blackjack Creek particularly, and you will, as individuals, work together to identify for the basins there what sort of actions might be top priority. So once you've got that in hand, you then implement those actions and you monitor them. The monitoring is the one thing that is not done consistently. For me, I'm a wetlands biologist. And through my career, most of the monitoring was done upon the vegetation coverage that was in those wetlands. And that was about it. You really didn't look at water quality too much. You really didn't look at whether that wetland was functioning as an entity. that was providing the functions that you thought it were. So to monitor results in a way, as Dan was referring to, that are meaningful and give you feedback as to whether the actions that you were taking are really effective is extremely important. So I think that's one thing that we just sort of talk about monitoring. Oh yeah, we're going to do it. We're going to collect water samples. But do you have a comprehensive program that's really asking the questions or addressing the questions that you have in your hypothesis? Are you going to improve or attain the normal or natural range of flow within that watershed? So as we all know, this can really help us guide future development patterns. And today when you do your exercise, I want the planners in this group to be sure that you look at the type of planning actions that you can take, not just looking at where you might be putting regional detention facilities, because I think one of the speakers mentioned, that was probably Dan, that you can't attain everything by just developing a stormwater retrofit system. We have to look to the future, and that's one thing the characterization is designed to do, to look at these rural or exurban lands that are going to be developing quickly over the next 10 years or so. And in addition, this will streamline the process for permitting if we have a plan that's clear for all aspects. I'm not just talking about stormwater, we're talking about how we're going to protect our wetlands and streams and what the actions would be for that. And of course, this works well into the comprehensive planning and our Growth Management Act and Shoreline Management Act. So one of the things that I have often found in my work is that when I look at wetlands or any aquatic system, the type of measures that I was implementing for cities that I work for when I worked later on at the Department of Ecology was pretty much site-specific and was driven, as you all know, by critical areas ordinance, or very specific measures that were sort of one size fits all for buffers and for different types of wetlands. But those wetlands were usually in basically 4 categories. What this doesn't do is that you don't really get at the root cause of what's causing that problem at that particular site. So this is what I call sort of symptomatic, as if a doctor was looking at a patient that came in, they had a certain condition. They would treat them for the temperature that they probably had by giving them some sort of an aspirin or whatever to bring that temperature down. What they're not looking at, what the root cause of that temperature might be. The same problem exists with our stream systems, that we're not looking at the root cause, and as a result, we're only perpetuating these problems further on. We're kicking the can down the road, so to speak. So being able to use a watershed approach to look upstream and see what the total impact is and what the solutions might be are extremely important. So you're not just treating symptoms, you're treating the problem specifically itself. Now, the result of this very sort of specific, site-specific approach has caused a lot of issues. One of those issues is that in the wetlands world, we've been finding that we only get about a 20 to 30% replacement of the actual functions on wetlands. So this, about 10 years ago, we became aware of this. There's a lot of literature produced around the country that demonstrated this. We began to look at the fact that we needed to be outside of the wetland itself in order to achieve full functioning. And part of the reason in the US, there is an approach among scientists which is saying that you have to look at the cause and effect and demonstrate that unequivocally through research, so you know every mechanical step that is in between that cause and its effect. Whereas in Europe, Canada, and Australia, there's more acceptance of the fact that you're not going to get there, especially with very complicated biological, physical systems. It's difficult to get all of those steps shown at a point or a degree where you have very good correlation with each of those mechanisms. So what you need to do is accept a certain level of risk. So maybe we understand that 60%, we're 60% certain that the relationship between the clearing of this forest is going to cause this effect downstream on this particular site. The reason I mention this is because in my field as a wetlands bio, this has caused my agency and other agencies and other local governments to be very conservative about their approach. Again, they will go to just saying we're going to have one size that fits all for buffers, one type of mitigation ratio, when in effect you may not need that particular buffer size or that particular ratio for that wetland because you don't understand the specific relationship between the cause and effect. And that's what this characterization approach does. It gives you a general idea about what your priorities might be in the watershed, and if you can accept that, you may get further instead of taking, as I point out here, a very conservative approach to mitigation. So these are the documents that we produced starting in 2005. They've been peer-reviewed, they've been updated, and our latest one is 2016. And if you're interested, you can go back to the PowerPoint and click on this, the links in there. So what I'm going to do now, this is the beginning of our exercise. I'm going to talk about how the characterization model is set up. And what I want you to do in the exercise is you're going to be taking, and many of you are very knowledgeable about the water cycle to begin with. But I'm going to explain how this model that we're going to be looking at might be used in order to make decisions on your part, specifically for Blackjack Creek. So we're looking at the delivery, movement, and loss of water in this cycle. And with this, we have controls on the landscape. Oops. So these controls on the landscape are things that regulate surface storage, infiltration, percolation, the storage subsurface, and then its discharge again. So precipitation, vegetation, topography, soils, and superficial geology are the 5 things within the characterization model that we apply. There's 2 models, and I heard that a question came up this morning about the importance model. So the first model I'm showing you is the importance, and we've taken the delivery, movement, and loss, and we've broken it down into these categories. So for delivery, we'll have precipitation and rain and snow areas. These are indicators on the landscape, and so with this modeling effort, it's an area-based ratio approach. So we look at the area, for example, that is in rain and snow, and we divide that by the total area of the particular watershed. So it gives you a value for each assessment unit, let's say within a RIRA, and then you take the highest value for that rain and snow area, and you divide it into all the other values, and you get a normalization. So you get a 0 to 1 score. And this is pretty much what we do with each of these indicators or of controls. So depressional wetlands, we take the area of depressional wetlands, which in terms of importance, they are a historic extent. So we look at the largest extent of wetlands based on the Surgo database, which shows us hydric soil extent, which is intersected with a digital elevation model, which is about 2% slope, and that will give us our historic extent or presumed historic extent of depressional wetlands. And then that will be combined with NWI and local wetland categorization or inventories if we have those. So that will give us our wetlands. We have the lake layer, and then we also looked at floodplains. So we have moderately and unconfined floodplains, which comes from another data set, SHIAP, which shows stream corridors as having these different segments, and we score those. So an unconfined is going to have more storage than a confined. So we might score the unconfined as a 3 and the confined as a 1. And that then again becomes another ratio which we apply and normalize. And all of these are not weighted at this point. We have decided not to weight them because we didn't have the resolution with this model to really say that one was more significant than the other. But we add each of these scores up, and you can then look at a surface storage map as well as look at a recharge and discharge map. And the idea behind this is the more indicators area-wise that you have in a particular assessment unit within a larger watershed, the more important that will be in terms of contributing to water flow processes. So that in a nutshell is our Model 1 or our importance model. So then we come to model 2, which is to look at alteration. How much have these indicators been changed or impaired under present conditions? So we're using current CCAP data, which looks at the landscape. And so this is all based on existing research that is available that demonstrates, as we know, that impervious cover has a tremendous impact. So we look at that area of impervious cover that's intersected within that particular watershed assessment unit. We look at forest loss. We look at dams. And then for overland flow and surface storage, we look at impacts to depressional wetlands. And again, the way to get at that, we realized that we had to intersect zoning density. So we scored zoning density as low, medium, and high, which CCAP provides that information for you. So again, you can score that on the order of the high density zone being a 3 impact, and then a 2 and a 1 for the lowest density. And then for recharge, we look at development intensity, and we're actually using the USGS recharge equations that they've developed for Puget Sound. And those actually do the same thing. They look at the high, medium, low density development, and they apply a coefficient to that, which reduces the amount of recharge based on the development type. We look at road density, and we calculate that on an area basis. And we look at well density, which is from the Department of Health, and impacts to floodplains and slope wetlands, which are an important component. We look at intersecting zoning with that as well. And impervious cover, finally, for loss or evapotranspiration was also applied. Now I'm going to show a short video to illustrate this. You'll probably be very familiar with these, but I think it's sort of nice to get an idea of what this might look like as the model runs through the importance model first. We're going to look at precipitation areas. So precipitation is that attenuation by the vegetation, the stem flow down to the litter and duff. So our flow is subsurface under a natural condition, historic condition. Then we look at snow areas, rain on snow. Another timing issue, very important for low flows in the summer and fall months. So we're really looking, as you all understand, attenuation at different times. So depressional wetlands and lakes, very important in attenuating in terms of that surface water. So these depressional wetlands are delaying and causing a desynchronization. And then our floodplains are very important. So for recharge and surface flow, we look at the different type of outwash and till, and we assign the different equations to those for recharge. And again, it's area-based for a particular watershed and CCAP. And then we look at subsurface flow, here illustrated by the gray areas. It's in a road cut. And water is moving downslope as shallow interflow, and then discharging downslope at slope breaks and at the base of the slope. And in this area, we probably get the greatest return in terms of discharge. And this is where you'll see more organic wetlands, organic soil wetlands. And here we are at the base of the slope. And then our hyperrheic zone, where we're getting discharge occurring, and the cycle starts over again. So that's our importance model, trying to look at the full suite of indicators that are on the landscape. Then we look at impervious cover, loss of forest. As example in the Chehalis, what happened with forest clearing. Again, no attenuation, rapid flow. And then we look at where we get development that occurs within these hillside areas, the change, attenuation, impacts to depressional wetlands, where we're looking again at this density of zoning. Development within floodplains, roads, fill, channelization. Again, this can be looked at again by the type of CCAP land covered. And then our development intensity. This is a large recessional outwash deposit in Issaquah, which huge storage and not knocking detention facilities. Most of that would be developed and lost by the impervious surface. And then the diversion of water by roads. The road density gets at this by looking at where ditches at the bottom of these slopes associated with roads will shift water into other watersheds and change the pattern of flow. And then finally we get back into our discharge of slope wetlands at the end. And that's our two models. So we can go back to the PowerPoint now. All right, so how do we combine these two models? We have this matrix that Michael showed this morning. So we've got on one axis, we have the level of importance from low to high, and then on the other axis, we have the level of degradation or impairment. So if the logic behind this is relatively straightforward, we're saying a place that has very high importance, so a large number of indicators that are present within that assessment unit and have very low impairment are an area that you're going to want to protect because it takes less effort and time and money to restore. If you were doing restoration, it's far more expensive and far more difficult. If you can protect these areas, you're certainly going a long way to taking that edge off of the change that might occur within the normal range of flow of your system. On the other hand, if you're over here with highest restoration, that's a place that is equally as important but has been altered quite a bit. The difference with this modeling approach is that instead of just looking at existing conditions as a wetland rating system might, it would look at these type of wetlands which might be in a suburban or agricultural area. They're highly degraded and they would be given a low ranking. They may be given a category 3 if you're familiar with wetland categories. 1 is the best, 4 is the worst. 3s, there's a lot of category 3 wetlands in Puget Sound. These areas are incredibly important in terms of restoring processes. So this is where this modeling approach differs in that it tries to focus attention on the need to look at these areas that are historically important and need to be restored. Then on the other hand, this modeling effort also recognizes that development has to occur. But you can put that development in areas that have the lowest probability of affecting water flow processes. So those would be areas that are low importance, have the least number of indicators on the landscape per area, and also have the greatest amount of alteration. So these would be your suburban areas and your urban areas. So you can see the shift that would occur with this modeling effort using it as a decision support tool that you're going to be looking primarily at these exurban, these rural areas that are in urban growth boundaries that are going to change dramatically over the next number of years. And then this category here are areas that aren't quite as important, but they're not altered. So you could call that whatever you wish, a second priority or third priority protection. But this might take more discussion in terms of whether development moves into this in a limited way, maybe lower density development. So that's the matrix, the decision or management matrix. And here's an example in RIRA 11, the Nisqually. So we're looking down here at the Nisqually Refuge, and we're looking up here at the headwaters, Mount Rainier. And you can see that most of the upper watershed, understandably, is in the protection category, which isn't surprising because it is forest land. It's not altered. It's certainly functioned at a very high level. We've got rain and snow areas. We've got precipitation occurring in the lower areas. We've got a lot of floodplain storage down in the stream, the large mainstream areas. But as we move into Eatonville, in this area, there's a lot of agriculture. And you can see the extent of the Restoration 1 and Restoration 2 areas. So the signal would be here to planners if we're regionally planning for a stormwater approach here, and we want to protect the Nisqually estuary, let's say, you would want to focus in actions up here. But this is going to take coordination between county and city government, and that's one of the things that is sort of the nut for us all to crack, because that's one of the most difficult things to achieve. So this informs the upslope areas, the areas within the actual aquatic system. That requires finer scale data. So you can't infer from this exactly what sort of measures you might take in stream, like the placement of wood, or how you're going to deal specifically with your sediment problem, but it gives you clues and directions as to how you might proceed. Okay, so here's our exercise, this Blackjack Creek ESA written report. was done with the Squamish tribes with Steve Todd. This was just completed this December. So the purpose of this study was actually more fish-oriented. The tribes wanted some type of plan which would provide direction and assurance in how they would protect the existing salmonid runs there. So we're going to take a little broader view. So I'm going to ask you, when you split up or you're already in your groups and you have some butcher paper here in front of you that you're going to use to work basin by basin. So the basins here are lower Blackjack. It's not very clear, but this is middle Blackjack. This is, we'll call this upper Blackjack. I think one of these is we'll have to look specifically. But if you can number these, I'd like you to sort of follow this scheme and come up with recommendations for each of these. Now, on the right, what I have is the importance model. The importance model shows the areas that are of greatest significance, again, have the greatest number of indicators. The largest areas for each of those indicators are in the dark blue. So these particular dark blue areas have higher importance. Now, this combines all the delivery and movement loss components of the water flow processes that I was talking about. The lighter blue areas contribute less, are not as significant. So to give you an idea about the general topography here, Highway 16 is running through here, and areas to this direction to the north and east of 16 are higher gradient slope going downhill and towards the city of Port Orchard. This area is lower gradient, sort of rolling topography, but that would be a component to keep in mind. So here's our overall degradation, so Model 2. So with Model 2, you can see that we have very high, the darker colors are very high degradation, moderate, and low. So the upper watershed looks like it's got less alteration or impairment occurring in it. And again, the resolution's not great here, but on these maps, the city's jurisdiction is primarily in this area, and there's fairly high density here. One of the maps in here actually shows you zoning. I think that's the next slide. And then we have rural residential primarily through here. So this gradient of development is moving down towards the mouth. And I've included the storage component. So this map, this run was specifically of the importance of storage. So you can see the storage or the dark, important areas are the dark blue moderately, and then the lightest blue are the least. And here's our basins again. And these are actually, again, I'm sorry this resolution's not great, but this is giving you the basin names, Ruby, Square Creek, I think this is the Square Creek area, and upper basins. All right, so then we have recharge. Again, the darker blue are the recharge areas within the basin that are most significant. The lighter blue are the least. So that's another thing to work into your analysis. And then this particular slide is showing you a change analysis, which comes from Ken Pierce's work, but the red is showing the highest degree of change, and I believe the tan and purple are less so. But you can see a pattern in this upper watershed, which is rural residential, is actually changing pretty quickly. So that will be another consideration. And this is our land use map right here, which the purple is our rural residential, and then down here we're into the city, higher density. This is rural protection. So that map will give you an idea of how to proceed on this. And then our water quality model, we actually ran this for this particular basin for Blackjack. And the way our water quality model works is that we actually look at the density of streams for the transport ability of an area of an assessment unit to transport sediment is based on how close that stream network is to that particular deposit that's erodible, and whether you have wetlands in there as well to trap and retain that sediment. So areas, for example, like this, and we're using the soil factors such as the K factor, slope and gradient, and cohesiveness of soil. So this has, the dark brown is very high export potential, whereas this lighter color means that you have lower export potential, and intermediate colors, tan colors, less so. So this is a way to sort of look at where in the landscape you have the ability to retain sediment and trap it. This is the NSPEC model, which is a NOAA model, and this looks at actual conditions based on running essentially a simple HSPF type model. So they're looking at water flow patterns and how altered the areas, and so this red area would have the highest degree of alteration, the green less so, and these tan areas moderate. So let's talk about what effect this type of change that's occurring in these watersheds has upon hydrologic metrics. So there's a number of metrics you can use: high pulse counts, you can use flow reversals, there's other categories. We've started to use high pulse counts because of the high correlation we've found with BIBI, and this is work that Curtis DeGasperi has done at King County. And to give you an idea of what a high pulse count might be for a creek that is in relatively good condition, so we're looking at Chico Creek here. It's down, and a high pulse count, by the way, is 2 times the mean average or average annual flow of a stream. And what they found is that these high pulses that occur, the more of them, the more likely that stream system is going to be disrupted and will not have as good an invertebrate colony or invertebrate species present. So Blackjack Creek is at a high pulse count of 8, and then we're going up here to Clear Creek, which is 12. And King County, in the work that they've done, you find creeks within King County in more urbanized areas that are up on the order of 30 high pulses per year. So that's kind of the range that you're looking at. Most streams, like on Vashon Island, you will find they're down on the order, such as Tahlequah and Judd, probably around 10 high pulse counts. So Blackjack is in not too bad a condition presently. So let's look at the BIBI data. This is Blackjack Creek here. This is the old 0 to 50 scale. This over here is the 0 to 100, and I've just doubled approximately, which is a BIBI of 34 for this particular series of years. And that is just a fair BIBI. And this is the baseline creeks in King County that they've used for RIRA 8, I believe, where they're looking at what the BIBI would be for the number of high pulse counts. So you can see that Blackjack, if we double it, is somewhere around here in the 70s. It's at the lower end or the lower slope of this trend line here. So one of the things that DeGasperi found on Bainbridge Island is that they had a similar problem where you have these urbanizing watersheds, but you don't have a lot of development within it other than clearing of forest, is that fine sediment seemed to be the aspect that was affecting the invertebrate population. So, oops, sorry about that. So just keeping this in mind about how we want to sustain this watershed in the recommendations that you're going to make. And this is just a diagram that was in the report that sort of gives a rough guide to about the relationship of those landscape controls, how they're degraded, so vegetation, loss of riparian veg, and large woody debris, and what the response of the process would be. So sediment, water quality, erosion of stream beds, and then habitat response, reduction of complexity of in-stream habitat. So this is just sort of a rough guide. And I want you to use this and the 2 models that I showed you to sort of go through answering these questions to see what you come up with, just out of interest. And we'll do this for about 10, 15 minutes. What time do we have we change over? Where is our 2:25? 3:25? Okay. So we'll do this for about 10, 15 minutes, and then have a couple of you come up and talk about what your approach would be to address these questions. So what are the key problems within this watershed? What does this watershed face in terms of what you've seen? What type of actions will best limit high flows and sustain low flows? I don't want you to look at just stormwater detention facilities. I want you to use green infrastructure. And then based on 1 and 2, what are the priority actions that you don't take? I want you to rank them per basin. And most importantly, what type of regulatory measures would you take? So we're going to go back to the basins. So you got butcher paper here to sort of generally just give a conceptual diagram on the watershed. Any questions? There's a lot of rumbling. Let's go to the map here quickly. So this area here, as you pointed out, is highly degraded. These areas are too, and there's a lot of residential development. This is within the city limits. So if I was looking at saying, what am I going to do first in terms of overall measures? If I'm going to do retrofit, would I retrofit here, or would I take actions here? Because this area is high in overall importance, and it's also high importance for storage. And I know you couldn't see on the maps, but there's actually a whole lot of peat wetlands in here, and then it becomes mineral, low slope retention areas. So of these two areas here, where would you take actions first? Yeah, exactly. And so one of the things that Dan was talking about is this transfer idea, which I think is great. I don't know how that's going to work particularly, but it would be nice to see monies arranged between city and county so they'd have a program where they could pick up these areas and be able to restore them, acquire and restore, because you're going to have more effect here, both with your sediment issues that are downstream, because you're going to be controlling flows. Oops, sorry about that. So that's really sort of the main point of this exercise, is to sort of arrange your thinking in a way that you are at the top end, you're really saying, what should I focus on first? Do I go for stormwater control here, or do I actually implement a program that uses land use planning regulations and an approach that's cooperative in order to get these areas protected? So, and I think I'm out of time, right? Got 5 minutes, okay. So the recharge, it also happens to be that recharge is very significant in this area, but also downstream. So I think some of the measures that Blackjack Creek group was proposing was primarily dealing with in-stream actions. And they're using Tim Beachy's works, and they're saying that one of the top priorities first would be to connect existing habitat that's within these stream systems so that you're getting lateral connectivity for fish. So that's only part of the picture. So that may help, but most importantly, you got to protect these areas in a way that you come up with a scheme that actually allows recharge to continue and storage to continue, because you will solve your sediment problem, and you'll probably maintain your flows at that high pulse count monitoring level of 8 per year. Otherwise, if this develops, which is primed to, because a lot of the areas over here, which I couldn't show you specifically, but if you look on your phone, just zoom in there, you'll see lots of subdivisions starting to go in adjacent here. But without controls that are coordinated between the county and the city, you're going to find that they're going to lose their integrity of the stream system. So this was really quick and probably too much to take in. If you have any other comments about how this works, you can call me or Colin Hume. We have our information at the end here. And this is the overall map, by the way, that is showing you where the restoration priorities would be, protection. And the lower watershed was an area really where you should continue to locate development, but that would sort of be the overall approach that you would take with this area as sort of a general guidance. So thank you. Any other questions?